I think we might get started. How was afternoon tea? Good? Nice? Awesome. We've got a couple more talks and then we'll get into drinks and nibbles and a bit more networking. Is everyone having a good day? Good. Awesome. Just want to take a quick moment to thank our sponsors. Without them, we wouldn't have today. Our main sponsors, ASX, AWS, and Franklin Smith. And a big thank you. Have we got any sponsors in our audience this afternoon? No? Okay, well, big ups to them. Let's jump forward a wee bit. So thank you very much to Eagle Technology for our afternoon tea. Welcome to the Trimble stage, and a big thanks to Trimble, our sponsor. If anyone's interested in finding out more about Trimble, there's some flyers just down here on the stage. Feel free to take one at the end of the session. I'm Sasha, welcome. I am a proud Canterbury Tech board member, so if you have any questions, feedback, anything like that, please do come and see me or anyone else in a shirt this colour. I'm also the director of a company called Follow My Lead, and we create training that helps people navigate new processes or software systems. So it means we get to work at the intersection of technology and people, ensuring successful software rollouts with confident end users. Before we boot up this session, let's run a quick last tech tune-up in this session. Stand up if you've learnt something new today or been given something to think about. Awesome. Cool, that's everyone. Okay, stay standing if you've met someone new today. Stay standing if you've had a coffee. Stay standing if you've had more than one coffee. Stay standing if you've had so many coffees that your smartwatch thinks that you're doing cardio. That might be me. Looks like we've got a few people running on Java. Okay, enough silliness. Let's get on with the presentation. I'm excited to introduce From Black Box to Open Platform, Transforming RiskScape into New Zealand's Natural Hazard Risk Engine by Russel, Garlick, Head of Projects at Catalyst IT. So Russel will share the technical journey of revitalising a legacy black box desktop application into RiskScape, an open source risk modelling engine with cloud-based collaboration capabilities. He'll cover key architectural decisions and development challenges in creating a platform that models impacts from natural hazards like earthquakes, volcanoes, floods and landslides. This talk demonstrates how the collaboration between Earth Science Institute and Natural Hazards Commission now supports use cases ranging from Auckland landslide impacts forecasts for emergency management to national earthquake risk assessments that determine NHC levy calculations for New Zealand home insurance. Russel is Head of Projects at Catalyst IT, where he has served as Development Team Manager for the RiskScape software development team over the past 7 years. He has extensive experience in software development and project management, leading complex technical transformations in the natural hazards and risk assessment domain. Welcome, Russel.
Well, good afternoon. Just before Sean's talk on projects this morning, we were asked a question about, what to share with someone next to us, the best or worst projects that we worked on, and the partner that I was paired up had a real doozy of a bad one. So I didn't get to share my good project, but I get to share it with all of you now, and which I think is pretty important because of what we're doing. So, look, I reckon it's fair to say as a country we've had a pretty rough time of it lately. We've all got stories we can share about earthquakes, cyclones and floods that we've experienced. Now here's the thing, these aren't just memories for us Kiwis, they're a pattern, and it's a pattern that's getting expensive. So let's talk some numbers for just a sec. Kaikoura 2016, we had a magnitude 7.8 quake, 2 people died, we had 618 injured. But here's the kicker, it literally cut the country in half. All land routes into Kaikoura were severed, the telecommunications link, the fibre optic cable ran up and down the railway line, the DR was on the other railway line, so that got cut. And the economic hit, well, from what I could find, it was estimated at around 450 to 500 million for the first 18 months. All of that from just 2 minutes of shaking. If we leap forward a little bit to 2023, we have Cyclone Gabrielle. We have 15 people died, and we had over 10,000 people displaced. 250,000 houses without power. The damage bill, still estimated, but between 9 and 14.5 billion. And seeing as I've been to Sean's talk, I know I'm going to round that up now to 15 billion. So that's our costliest non-earthquake disaster ever. And just this year in the Nelson and Marlborough area, they copped flooding that was the worst since 1877. So that's 148 years. An emergency worker died, there were hundreds of people displaced, and now land that has been worked for generations is too unstable to be productive. So here's what I'm getting at. As a country, we've spent over $50 billion on disasters in about the last 15 years. And they're getting more frequent, more severe, and frankly more expensive. And that's just the monetary cost. This gets compounded by the time we start to consider the disruption and stress that these events add to people's lives. So the question I want to put to you is this: what if we could get better at making decisions about how we could reduce the impact now from these events later on? What if instead of being on the back foot cleaning up from disasters, we could actually get ahead of them? And that's where RiskScape comes in. But let me back up and give you a little bit of context. So after disasters like the Christchurch quake series and a series of quakes in Turkey and in Japan, the international community got together and said we need to do better. The Sendai Framework is a UN initiative, and it basically says priority one is understanding disaster risk before it hits you. So New Zealand has signed up to this as a country, and we've incorporated it into our National Disaster Resilience Strategy, and that says the same thing. We want evidence-based decision-making, not just crossing our fingers and hoping for the best. So about 15, 16 years ago, RiskScape started as a research program. There was a joint effort between GNS Science, who know all about rocks and earthquakes, and NIWA, who know all about water and weather. It was funded by MB's Strategic Science Investment Fund, with backing from what was then the EQC, who are increasingly keen on us all making better decisions about where we put our houses. The vision was pretty straightforward. Instead of being reactive, let's get predictive. Instead of going, oh, bugger, that happened again, let's model out what happens if the Alpine fault goes off, if we get another Gabrielle hitting different parts of the country. So replace gut instinct with science, which sounds obvious, but trust me, it's been harder than it looks. About 7 years ago, alongside the science, there was the RiskScape desktop application that had been built in-house by those teams. So we had some solid science and some really smart people working on it. But here's the problem. It was a black box. All the data, all the vulnerability functions, all the ways that it calculated risk were hard-coded into the application. So if you wanted to model something new, you didn't just need a researcher, you needed a programmer. You wanted to add a different type of building, rewrite the code. A new type of hazard, rewrite the code. A new data type, you guessed it, rewrite the code. The researchers were spending more time fighting with inflexible software rather than doing the science. So GNS and NIWA put out a tender. Can someone build us RiskScape 2.0? Make it flexible, make it usable, but keep the science solid. We won that tender, and as soon as we started, we knew this wasn't going to be a traditional software project. We couldn't just gather some requirements, write some code, and hand over a finished product. This is an ever-evolving space. So we knew it was going to be iterative, experimental, collaborative work. So at the beginning, we made 4 key decisions that I reckon made all the difference. And that first one was that everyone does Agile. First thing we did before we wrote a single line of code was run Agile training. Not just for our development team, but for everyone, all the stakeholders. The scientists, the engineers, the researchers, our developers, the project managers, the lot. We ran basic Agile training and product owner training, and everyone got certified. You might think that's a little bit over the top, but here's our reasoning. We needed everyone to understand that we're going to build this thing together iteratively. No big upfront design, no here's the spec, build this. We were going to build, test, learn, and adapt. And for that to work, everyone needed to speak the same language. Now, luckily, we were working with scientists who are used to hypotheses and experiments, but they're not so au fait with software sprints and retrospectives and that kind of thing. Getting everyone on the same page meant that we could move fast without constant confusion about why we needed to change direction. And during that training, we would run multiple projects, we would build products, and from my position as project manager, this was a great way of auditioning not just my project team, but the client as well. They gave me insight into how people were going to work together, what was their approach to problem solving, who jumped straight in, who was more deliberate, who stuck to their guns, and who was more open to new ideas. And this is really useful information to get before we started the project proper. And it's fair to say not everyone who went through the training survived into the project team. And again, I'm going back to what Sean was saying, it was somewhat by accident that we ended up with the right people out of this process. The second big decision, and this is where we probably caused a few heart attacks, was we proposed starting from scratch with the code base. Yeah, now look, I know every developer hates working on legacy code and thinks that new code is better, I get that, but this just wasn't developer bias. We looked at the old system where everything was hard-coded and the architecture just wasn't there to make it general purpose. So we asked GNS and NIWA to risk 6 weeks, give us 6 weeks of our time to build a prototype that supported the spatial processing workflow that they wanted. Being scientists, they like a good hypothesis, they agreed to an experiment, and in 6 weeks to prove that we could build something more flexible than what they had. If we failed, they'd only lost 6 weeks of time and a little bit of money, but they would have learned about what was possible. If we succeeded, we had a new foundation to build on. And that prototype has become the core of what we have today. So I guess the lesson here is sometimes you need to take a step back to take a couple of steps forward. The third decision, and this one really surprised people, is we questioned whether we needed a user interface. Now look, I love a good UI. I have a background in user interface design, user experience design. It matters to me whether something is a radio button or a drop-down list. You know, I like a good use of negative space. But here's the thing, building a good UI takes focus, real focus. And at this point, we were more focused on getting the modeling engine right. We wanted to give the modelers more functionality so they didn't have to pre-process data before using our system. Ideally, we wanted it to be faster for them to build the models in our software rather than having to muck around externally with GIS and scripts. So we proposed no UI, just a command line interface. Your model becomes a text file. You run a command, point it at some files, and off it goes. And our clients agreed. For GNS and NIWA, or as we know them now, Earth Sciences New Zealand, it was more important to them to have the modelling features than to have a pretty interface. And this proved to be a masterstroke, because for the first 3.5 years, there was no UI for RiskScape. And that meant that we could rapidly build out complex modelling and geoprocessing functionality without the overhead of having to build a complicated UI. There was no discussions about button placement or colour schemes, no pixel shuffling. It was just, does the function work? When we eventually did build the first UI, it was more like a command line wizard, more like one of those text-based adventure games from the 80s and 90s. You're in a dark forest, you can go north, south. Yeah, except it was, you want to model flood risk. Point us to your building data, point us to your vulnerability functions. Sounds ridiculous, but it worked. It meant the researchers could get started quickly and we could focus on the engine. Now, of course, these days we do have a UI, a web-based platform, but that was much easier for us to build because we went through this process of understanding how the modelling worked, and then we could reflect that in the UI. Decision 4 was to open source the model engine. A big problem with that first black box was that it was presented as a compiled desktop app. The user interface for it didn't give away how the model was working, and as a result, many researchers did not trust it. Open sourcing the engine meant that we could get it into other researchers' hands easier, but more importantly, it was about trust. Anyone can go and download our code and see how it works. Models are not hard-coded inside the app, they're provided as text files. Everything is done in the open. Disagree with the result? No worries. Tell us where the working is wrong. Hell, submit a patch if you like. So with those decisions made, what did we build? Instead of a black box, we built what we call a flexible data processing engine with some key features. So we have these things now called model pipelines. I want you to think of it like a recipe, but for risk analysis. You define a series of processing steps, bring in your hazard data, manipulate that, bring in your building data, do some spatial analysis, calculate the impacts, spit out the results. But unlike the old system, you can change any steps, you can add new steps, you can write your own functions. We have an extensive suite of geoprocessing functions built in. And so this is where you can do spatial filtering, like show me only the buildings and flood zones, and give me those. Or if we're modelling out roads or power networks, which are often presented as lines, let's do some buffering to include the area around that, the verges, etc., which are, as part of that analysis. We can do things like segmenting. So if you've got a roading network, you can break that up into chunks, either 10, 20 metres long, or by territorial authority or region, and do your analyses that way. So we have the GIS tools built into the risk analysis. When it comes to spatial sampling, this is all about how we extract that hazard data where it matches up with our building footprint. So most systems, what they will do is they allow you to sample at the center point of the building. But we also allow you to choose like the nearest neighbor, or, and this can get really useful, analyze all the hazard values that intersect with your object, and then decide how you want to treat that. And this is really important when you're starting to model out assets such as farms and forests, so you can get a better picture of how the hazard is impacting it. Like some of the other big players, we support deterministic modelling, so that's what happens when this specific scenario with this ground shading by this quake and these buildings, and so we can get the impact, the damages. But to get risk, we need the probability, and so that's why we have 3 different types of probabilistic analysis, and this allows you to evaluate the risk around the likelihood and impact from a hazard and get those all-important metrics the insurance companies like average annualized loss. So we can do things like a hazard-based, so where we know the probability of events, so we've heard about the 1 in 10, 1 in 20, 1 in 50, 1 in 100-year floods, we can use that to model out. Or we can look at event-based, which is more what you need to do with earthquakes, where we will take thousands or even millions of scenarios and model those out to build out our curves. And then we can weight-base those events for complex things like volcanic eruptions, where different scenarios have very different probabilities. And here's where we get different from other tools, is that we support multi-hazards. So most risk software does one hazard at a time. It will give you the earthquake or the flood. But in the real world, hazards interact. What happens when earthquake damage makes buildings more vulnerable to the tsunami that follows? What about compound events? You have a cyclone plus a king tide plus river flooding all happening at once. The impact from multiple hazards don't just add up, they interact in complex ways. And that pipeline approach we developed supports this type of modelling. Right, enough theory. Let me show you how this works in practice. Now, this is where I would have liked to have handed over to one of my colleagues from Earth Sciences New Zealand, but they are in Fiji at the moment, running a RiskScape workshop, so we're stuck with me. Let's start big. Roading infrastructure, critical to our economy, but vulnerable to sea level rise. So the question is, what is it going to cost us over the next 100 years? This is spatio-temporal modelling at scale. We're calculating potential losses every 10 square metres across the exposed road network over multiple sea level rise scenarios. And here's the important bit, we're accounting for vertical land movement. And it turns out that that matters a lot. In areas where the land is sinking, the impacts of sea level rise could be felt 10 to 20 years sooner than if you just look at the sea level rise scenarios alone. Some places like Wellington and parts of the South Island are more exposed because they're close to the coast and the land is sinking. And RiskScape was being used to model out different adaptation strategies as well. So should we build stronger infrastructure or should we change how we use the roads? And so now transport planners have climate-informed information for making their investment decisions. During Cyclone Gabriel, we had a massive rain event where we had torrential rain, landslides everywhere. Communications are down, we can't get field teams in, and emergency managers are basically flying blind. Where do we send help first? So the GNS team rapidly deployed a new model pipeline that incorporated rainfall forecasts twice a day into their landslide hazard models. It evaluated not only property level impacts, but it also looked at the roading network, which segments of the state highway were exposed and at risk. And here's the validation. When the insurance claims came in after the event, they matched our forecast spatial distribution very well. Emergency managers had used our outputs to help guide their resource deployment, and it was the first time we'd done real-time risk modelling during an actual disaster. But there was a limitation. It needed one of our scientists to be manually cranking the handle on a laptop, and that's something that we're working on improving. If we go into the Pacific, I think our Pacific neighbours are much more alert to the impacts of climate change than we are here. So 6 Pacific nations, the Cook Islands, the Marshalls, Samoa, Tonga, Tuvalu and Vanuatu, they're all part of the MFAT-funded Partner 2 project to help them understand climate-related coastal flood risk. So what we've been doing is national-scale flood modelling for each country, for all of these sea level rise scenarios for up to 2 metres, and we have built up risk profiles for not just populations, but buildings, cropland, and critical infrastructure. The goal is to help these countries to make their own climate adaptation decisions based on solid science. The Natural Hazards Commission, they've adopted RiskScape as their official loss modelling tool. They call it PRU, and they use it to get insurance on the global market to cover the first 300k of all of our houses. And they got a good test at the exercise Ruwhenua last year, which simulated a magnitude 8 alpine fault rupture. During that exercise, the NH team used it to calculate residential losses and provide advice to decision makers in real time. We're in the process of expanding PRU just out from earthquakes to include volcanic activity, liquefaction, tsunami, and landslides. Right now, we're working on the Auckland volcanic field. And if you've had to deal with any smugness from our friends north of Bombay Hills, just remind them they are sitting on a time bomb. Very low likelihood, but super high impact. All right. Right, so where to from here? Now, I said earlier that we're limited by needing someone to manually crank the handle and run the models. We've been working actively to solve that problem. So we've got prototypes and testing where we can generate impact forecasts from GeoNet earthquake shake maps. When the earthquake hits, the system pulls in the shake data and it starts modelling without any manual intervention. It will produce tables and maps built on the fly and send out an email notification with that data. Still in testing, but we have it working. And we're part of the way through the Sliding Lands Endeavour program, working with Earth Science New Zealand and others on a real-time landslide impact forecasting network for the whole country. It's designed to take that Cyclone Gabriel work and productionise it, to take live weather data and land data and generate those impact forecasts automatically. From a technology side, we're looking to replace that command prompt with a chat prompt. But here's what I want to stress. This isn't just a technology project. The huge strength of this work has been a collaboration between the scientists and the technologists. We're constantly learning from each other. The scientists understand how the disasters work and behave in the real world, and we understand how to build systems that work under pressure. When you put those together, you get something much better than either group could have built alone. So to finish off, look, disasters are getting worse, but we're building better tools to understand and prepare for them. We've shown the science works, we've shown the software works, and now we're working on making it faster and more automated. The collaboration between science and technology, that's what makes this more than just another software project to me, and that's what gives me the confidence that we're on the right track. Because the next big one is coming, but with each iteration, each prototype, each lesson learned, we're getting better at being ready. Thank you. Oh, yeah.
Q&A.
Righto.
Come on, take a seat on the couch and grab a mic. Thank you very much. Very interesting. I have got one question here. Is Celeste... Oh, perfect. Just double checking. Oh. With the rise of vibe coding and disconnection of end users from source files, can you comment on getting stakeholders to invest in a maintainable code base?
Great question. I feel a bit on the spot. As a vibe coder myself, I think one of the things that's important, particularly for the National Hazards Corporation, is that everything that we do is completely auditable. And whilst we're experimenting with code generation and looking at how we can make use of that, it's just a little bridge too far for them to be thinking about that the code base is going to be suddenly just going to switch on them because the agents start regenerating. So in our use case, we're looking at it around the sides, but there's still in the core. We've just got to have human eyes going through and doing that.
Nice. We've got questions coming in now. How did going no UI impact uptake in the early days? Did that impact accessibility?
It did, but a lot of the researchers in this realm are all programmers. So they're used to working with Python, and a lot of them would be doing this kind of analysis, but coding it out by hand in GIS. And so one of our researchers, it would have been 6 months in, came to us and said, with what you guys have already done, it would take me 2 weeks to do this manually, and it's taken me a day, or half a day, because all the tools were there. So I guess it was a conscious decision because we knew that there'd be some people who wouldn't be happy with the code interface, but most of those people don't want to interact with the model. They want the outputs, they want the maps, they want the data. They don't want to change the model itself.
You've made the engine open. How open are your partners to making the data open and available?
Yes, this one was in the news, I think, a couple of weeks ago. That's not something I can comment on. All I would say is that I think we may have broken how we fund science in New Zealand, and that we have a situation where our science institutes are given public money, but they're also requested or required to return a profit, and so this sets us up in conflict. I look over to Australia where they are purely public funded and they can make this data freely available because they don't have that constraint. Mm-hmm. And I just would like it to be the same here.
Mm-hmm. Yeah, I can imagine. What was the biggest change in shifting from the previous problems with hard coding in the old system? How do you continue to avoid this practice with the new version, especially where it might appear to be a convenient temporary option?
Well, we didn't have much to do with the original system at all. That was built in-house by then GNS and NIWA. It's just checks and balances within our own team. I've always said the best programmer is a lazy programmer. It's someone who doesn't want to come back and have to re-look at the code. So it's just an ethos that we've built into our team. Is let's just do it. Let's make sure it's general purpose. Yes, there have been times to meet deadlines for proof, for example, where we have had to go through and maybe hard code some stuff. But we're lucky that we have clients that recognise the value in coming back and generalising those solutions later on. So,
Yeah, nice. What do you think the challenges might be with incorporating RiskScape into a common operating platform?
I'm not sure what someone means by that one. In terms of our platform, well, everything's API driven. So, one of these days we will get round to finishing the API spec. It's mainly used internally by ourselves at the moment. So, mea culpa there. I think that would be the one thing, that would be an area of work that we'd need to finish off. It is the web-based platform is definitely built in that way, and expected that that's something that we would like to be able to plug into other people's systems.
Yeah. What's next? What's the plan for the future?
Right now, a big thing that we're looking at is that making our researchers, and when I talk about researchers, I'm talking about research institutes and universities around the globe. A lot of them, they want to use like public AI to generate RiskScape pipelines. So things that we're looking at doing is how we can, it's just even basic hygiene, how we can make our documentation more easily imported and read by those systems. We're doing things with some prompts and that kind of thing that we can provide to people to give them the context. If you go to ChatGPT now and tell it to build your RiskScape pipeline, it'll do something that looks about right, but I can tell you it will not run. I should say there's a very, very low chance it'll run. And what we're looking at doing is, there's a lot that we can do just with prompts, a prompt library that give people that context. So that's kind of the first bit that we're working on.
Yeah, cool. Awesome. Thank you very much.